Hello, fellow engineers and science buffs. I've recently retired from a long engineering career. One of the first things I did upon retirement was to dive into climate science. I've always wanted to get a grip on it. Personally, much of my retirement fund is in oil and gas securities and nuclear energy. So science is a very important context for that. I didn't want a partisan answer. I wanted the technical answer. And of course, engineering is nonpartisan. I thought I could knock it out in less than a month. It took me about 6 months. I found that the information out there was either superficial, political, or required PhD level skills. And it was certainly not at the pragmatic technical level engineers appreciate and expect. As I studied, I did my notes in PowerPoint because of a career habit. I freed them up for this and removed all but what I think is essential. Yesterday, I gave this talk to 150 engineers via a Society of Petroleum Engineers event. This version is effectively the same talk with the same slide deck. So, why understand the technical? I feel like we engineers should understand climate better than we do. We have the technical skills to understand it that the general public doesn't have. We can help lead a productive narrative from a quantitative perspective. I have a picture here of Homer here. He's making a future prediction with no analytical thought, as is his nature. I think there's a lot of people on both sides of this topic that let their inner Homer guide them. So here's my outline. From the engineering world, I've seen us tackling difficult problems with messy data and having to make predictions. That's what we do. I've used a similar engineer's approach workflow. I hope you see and enjoy the parallels. So the engineer approach I'm taking here is starting with what are the basic underlying physics? What do the models predict? What are the confidence intervals of those models? How does this compare to actuals? And how do the changes compare to system noise? So weather, temperature, noise. The topic order is basically a CO2 backdrop, and then get into the theory, the greenhouse effect, and actually how to do basic temperature calculations yourself. Um, then I'm getting into kind of actuals on temperature, on precipitation with precipitation theory, and sea level with sea level theory. Hopefully, at the end of this, you can be the person in the room that knows the numbers and their context. So let's start with some CO2 basics. CO2 is the gas of life, in my view here, for plants and for us. Without it, we perish at about 150 parts per million CO2. Fortunately, feedback loops seem to prevent this. In the top right here, you see CO2 levels during the last ice age cycle. So this is the last 800,000 years. I think the ice age cycles have been the last couple of million, but there's really good data for 800,000 years. And you can see the CO2 level kind of cycling from maybe like 280 parts down to like kind of like 180. So not below 150, but getting close, going back up, down. So maybe there's like 10 cycles here, or 8 cycles over maybe 100,000 years a cycle. Um, what's driving this cycle? Well, part of it is thinking about, at a big picture, what does the cycle look like? Well, fortunately, volcanoes are inputting carbon dioxide, have been inputting carbon dioxide into the atmosphere, more or less continually, year by year, for a very long time, history of the Earth. Um, and they're putting out about zero point 0.3 gigatons a year. So starting to work with numbers, gigatons is a billion tons, and gigatons come up a lot in climate science. So zero point 0.3 would be a typical year from volcanic activity. Obviously, there's some big volcanic events that have happened over the ages, but that's a good rule of thumb. Now that CO2 ends up getting consumed. That's why it just doesn't keep going up and up. It's kind of going in cycles. And there's an organic cycle and an inorganic cycle. The organic cycle has to do with plants and ocean life, and it's kind of consuming the CO2. And when these critters and plants die, some of that carbon ends up being sequestered. At the bottom of an ice age, when it's really, really cold and miserable, when you're really worried, you're kind of down at the bottom of one of these little dips here, um, they start consuming less, and that's helpful. Um, and then there's an inorganic cycle as well. So, rain absorbs carbon dioxide from the air. and um, that carbon dioxide, it's dissolved. It has a geological process, weathering rocks. And as a product of that, bicarbonate ions end up going to the ocean, and those are used happily by seashells and things, which is basically, they fundamentally are also sequestering the CO2. And that process also slows down a lot at the bottom of an ice age. Basically, there's a lot less rain at the bottom of an ice age, kind of more snow. So anyway, that's nature's wonderful dance over the last million years plus with CO2 levels. For context, we should probably step back and look maybe 60 years from the dinosaur times. So here, maybe 50 million years ago, we were, particularly hot, about 10 degrees Celsius warmer than we are today, and the temperatures gradually sliding until we got into the ice age cycles here, where average temperature was 4 or 5 degrees colder than we are today. At the same time, carbon dioxide levels were about 1,500 parts per million back 50 million years ago, and those have also been gradually sliding until we got into the ice age cycles where they drop, dangerously low and then bounce back up and down. How the heck do we have all this climate data? Well, from scientists drill ice cores. Up to 12,000 feet deep. There's a lot of ice, particularly in Antarctica. It's extremely thick. And they've successfully cored down to 800,000-year-old ice. They use wireline retrievable cores, and they pull out these cores, which is like a long tube of ice, and they can typically see these tree layers, these tree ring-like layers of ice, which is kind of the seasonal ice layers. And from that ice, they can calculate all kinds of interesting things. From the air bubbles entrained in ice, they can directly measure the carbon dioxide, so they can see those swings just fairly obviously. But also from the isotopes, they can actually calculate temperature of when that ice formed and was laid down. And they can also carbon date the carbon, for example, in the dust particles. And so they can calibrate volcanic events in layers kind of for different places they drill, for example, Greenland, Antarctica, or other glaciers in other places, and they can calibrate all the layers. And they can also measure other gases. It's really incredible. To me, I think this is particularly adds credibility to a lot of the scientific models simulations, because they actually use these models to history match, so they can history match the cycles as you go in and out of the ice ages as CO2 levels change and other things are changing. So what's the deal here on these ice ages? Why does that temperature plot look so different in the last 2 million years than the more apparently stable period before that? And it's because there's been this tipping point between the world, being a lot of it covered in ice or the ice melting. And let's talk about how you make an ice age. So, let's say it was the first one. CO2 levels had been gradually dropping as the sequestering, was occurring, as you saw earlier in that slide. And then there's these orbits around the sun of the Earth, and those they're not always the same. They gradually change over the centuries, and about every 100,000 years, the orbit spends some time, many hundreds of years, where Julys are particularly cool at the Arctic Circle. This causes less polar ice to melt in the summer. So basically, the world from space looks whiter because there's more ice. That's reflecting more sunlight back to space. And so this cools the Earth just a little bit the first year, just a little bit more the second year, etc. And so as that Earth is just a little bit cooler, the oceans get just a little bit cooler, and cooler water can absorb more carbon dioxide, just like a a cooler can of Coca-Cola can absorb more, can hold more bubbles. You heat up your pop and it loses the CO2. Same deal. Um, and and so the cooler ocean absorbs a little bit more CO2, so CO2 levels drop a little bit, which cools the earth slightly. And again, at this time period, Julys are particularly cool. So the polar ice caps expand a little bit more, reflect a little bit more sunlight, and this whole thing spirals down, and you get one of these ice ages. Um, and then to warm back up, remember from 2 slides ago, so the Earth sits at kind of in this cold state for a long time, um, and life's tough. At the same time, these volcanoes have been very helpful, and they're continuing to emit carbon dioxide, and consumption is probably a little bit less now because of the ice age state. And so CO2 levels come up a little bit. And then that will overlap at some point with the orbital cycle, which is the opposite. So Julys are particularly warm at the Arctic Circle. And so then the ice shrinks, particularly a lot, in a year. And the Earth, that makes a little bit less sunlight reflective space, a little bit more stays on Earth. And the whole cycle goes and goes and goes until you get to one of these interglacial periods, which is where we are happily today. Um, and and there you have it. That I guess would be the climate news, this ice age mechanics for the last couple of million years. And hopefully you've got some context of climate since the dinosaur days. Let's talk about modern CO2 levels with that context. Hawaii has the best and cleanest long-term data set. And I'm kind of showing that here. The left graph shows CO2 levels in parts per million from 1960 to the present. You can note both the concave uptrend, and then it's becoming a little bit more linear for about the last dozen years. And the slope numbers are shown at around 2.5 ppm per year in the last dozen years or so. Remember that 2.5 ppm per year number? It's going to come in pretty handy later as we do a lot kind of more calculations. On the top right graph, you kind of have the data for the last 4 years, just so you can really see what's happening seasonally. You can see the big swings. The seasonality is due to northern hemisphere plant activity in the summer. I'll talk more about that later. The black line is the seasonally adjusted average, which is what people kind of focus on. I've marked COVID, where we had about 6 months of carbon austerity here on Earth. It turns out the impact was about the width of the black line, which speaks volumes about the difficulty in reversing this upward trend, because effectively the amount of carbon that was released, percentage-wise, it wasn't that big of a reduction versus a normal year, because there's a lot of carbon that's going up. So let's do material balance calculation to try to make sense of all this. Let's tie these numbers on the top left, i.e. the emission numbers, the anthropogenic, that's the human-caused emissions, with the slope. So the top left graph shows global emissions. Note the flattening trend at about 41 gigatons per year in the last dozen years or so. Where this goes in the future drives the magnitude of future changes we might expect. But for now, let's do a bit of math on the historic values. It's a very simple material balance calculation, easier than the oil and gas material balances that I'm used to in my career, where we've got phase changes and fancy stuff. This is basically simple single phase gases. So basically what you do is I've got the calculation for three different years for 1962, which correlates to the left first blue box, where you get 16 billion tons per year, and then 23, and then 41. So you just convert that to moles, and then you compare that to the size of the Earth's atmosphere. And from there, you can calculate basically how much the ppm should be going up per year. Pretty basic stuff. And then you compare those to the slope numbers on the graph on the right, and you see they're different. They're about half. What the heck's going on? Well, fortunately, Plants and oceans have been absorbing about half of the CO2 that we've been emitting. So go plants. Yay, nature. Um, so let's get into a bit of climate science, particularly warming science, so that we can teach you how to make calculations. Let's start with thermal radiation. Remember your grade 12 physics. Everything that has temperature is radiating energy, including you, your desk, your coffee cup. It's the heat you feel when you're standing close to a bonfire and that heat's coming at you. I think you all know this. And if you remember the equation, this radiation is proportional to temperature to the power of 4. So there's not a lot of things that are t to the fourth, but this is. So hot things emit short waves, like the sun emits white light, and cooler things emit longer waves, like planet Earth emits infrared. Um, so the Earth sits equilibrium more or less with visible light coming in. So in the top right picture there, I'm just going to move my head. Um, so you can see the sunlight's coming in, and then the Earth is radiating out. And that, in the long run, is in balance. Otherwise, the Earth would melt down or get super cold. It's got to be in balance. So it's more or less in balance. Now let's talk about how greenhouse gases trap radiation. So there are gases in our atmosphere that they interfere with these long waves that are trying to leave the Earth in that previous cartoon. So these long waves, they get captured, they're heading out, and some of them get captured, and then the energy is re-emitted by those gases in the atmosphere. Again, long wave radiation. Um, and it's all about the vibrational frequency of these different gases in relation to the wavelength and frequency of, of the radiation. So let me explain. So the top right, we've got nitrogen and oxygen. So on the top left, you see that that's what most of the gases are, right? So think of them as kind of dumbbell shaped, and they're vibrating back and forth kind of really fast. That vibration frequency doesn't sync with the slower long wave vibrational frequency of the infrared heading up to the atmosphere. So they don't capture these long waves. These radiation just zips right through. With some gases of note, water vapor and carbon dioxide, and we'll talk about others as well, they have kind of bent shapes and they vibrate more in a bending motion. That kind of vibration is a much slower vibration, and that is able to synchronize with the frequency of uh, synchronize or resonate with the frequency of the emitting long waves. So there's a diagram below which kind of shows wavelength versus how much is being absorbed trying to go through our atmosphere by water vapor, which is the blue parts of it, and carbon dioxide in the red parts of it. So you can see here that, like, for example, there's frequencies. You've got wavelengths here, see between the numbers 5 and 8, where water vapor is basically absorbing all of the infrared radiation trying to get out. Whereas here, there's a big hole, and it's able to zip right through. And here, carbon dioxide and water vapor kind of work together, and both of them are absorbing the long wave radiation. This diagram is a bit of an oversimplification because vibrational frequency, as you know, is a function of temperature, things like that. So it's not completely that simple, but I think this is directionally how you want to think about it. So let's get quantitative. What is the insulating value of the extra carbon dioxide or the carbon dioxide period in the atmosphere? But let's talk about the incremental carbon dioxide. People have been passing light through gases for almost 200 years to measure the effect. Draw your eye here to John Tyndall set up to measure absorption of thermal radiation by various gases, including water vapor, in 1861. So way back there. this part of climate science is very mature. Um, the plot on the left shows a modern absorption model in watts per square meter of, for different frequencies, basically at the top of the atmosphere looking down. So the the red lines are showing you kind of how much is going up trying to get out, and then the blue and the green lines show how much is actually getting out. Um, there are two lines, a green line at 300 ppm, which is similar to pre-industrial carbon dioxide levels, and a blue line which shows a doubling of CO2 levels to 600 ppm, which is where we will be in about 70 years if we keep emitting about 2.6 ppm per year. Notice how for most frequencies the lines are on top of each other. So basically, the CO2 makes no difference. You can't even see the green line because it's hidden underneath the blue line. But for a few frequencies, you see more absorption where the CO2 is making a difference. And so the blue line is below the green line because it's absorbing more. The extra amount of filtering, so basically you think of it, the area under the curve here, it's 3.4 watts out of almost 300 watts. So it's just like a little bit more than 1%. It's a measly 3 watts. So you think about, like, those little night lights that you might have in the hallway. It's like one of those night lights over a square meter of extra heating, extra energy captured by the atmosphere. Um, this little bit of extra energy is called forcing. Um, Forcing is central to climate science. The climate guys do all their talking is about forcing, and it's about watts. They're like engineers. It's all watts, 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 not degrees Celsius, because this is the extra energy that drives all of the climate models. There's an equation at the bottom that approximates how the atmosphere forcing changes with changes in CO2 levels. This is a very stable equation. It's one of the few well-anchored equations in climate science. There are many places I'll show you where skeptics can push on climate science. I don't think this is one of them. There's a long history here, and it's very stable. So the equation shown here, delta F equals 5.35 times the log of the concentration ratio. And that's the concentration of CO2 levels now divided by the concentration of CO2 at the reference point of 278 parts per million. So for today, where we are at about 420 ppm, we get a CO2 forcing of 2.2 watts per square meter. So let's put this 2.2 watts per square meter in context. And you have to start with something that's called the Earth's energy budget. Don't get a coffee right now. This is key. So this is the energy balance of average Earth at the current climate condition. So this is watts averaged over the whole planet, all the way around, day and night, 365 days a year, poles to equator. So like a sunbeam is 1,320 watts per square meter, but average day and night, poles to equator, etc., that converts to 340 watts per square meter of sunlight hitting the Earth. That makes sense to you. And about 100 of it is basically reflecting right back out as white light. And this is the shortwave stuff we were talking about earlier. And so that doesn't really enter the warming equations. It's just gone. If an alien is looking at Earth, he's got 100 watts per square meter leaving it, and that's what he sees. It's not warming the Earth. It's providing a visual for the alien, okay? So that leaves 240 watts keeping us warm. At the same time, you have almost 240 watts leaving the Earth as long wave radiation out the top of the atmosphere. So you can spend a lot of time looking at this graph. You can go ahead and pause it if you want. But one thing I want you to note is that there isn't quite 240 watts per square meter leaving. So 340 minus 100 is 240, but there's only 239. Well, what's up? Well, the Earth has got a little bit bigger, a little bit warmer because of a little bit of extra CO2. And so the warmer atmosphere is warming the ocean just a wee little bit. Zero point 0.7 watts per square meter is going into the oceans. So basically, there's only 239 leaving. Um, this is the unsteady state part of the current energy balance. More on that later. But if you think back to the early equilibrium slide where we had a picture of Earth with sunlight coming in and radiation going out, and I said it was in equilibrium. But when there's a change going on, it's not in perfect equilibrium. It's almost in equilibrium, but not quite. Um, the second thing I want you to really notice is how hard the Earth has to work to emit long wave radiation. With or without climate change, it's still the same. That it has to work really hard. So here you can see the Earth is emitting about 398 watts, from ground level, pushing up in an atmosphere to get 239 out the top. And the reason it has to work so hard is the atmosphere is pushing so much down. You can see it over here because it's basically absorbing a lot of these long waves. And then the warm atmosphere is sending this down back at you. Just like on a cool night, if it's super clear on a cool night, it gets a lot colder. There's less water up there. And then on a real cloudy night, it doesn't cool off as much because you get more of this long wave radiation coming back at you. So let's try now to do a little bit of simple math. I want you to start to get a feel for the kinds of things that climate models do and think about. How much warmer should 2 watts or 2.2 watts or whatever make the Earth? So it's fundamentally a radiation problem. So let's do a simple radiation calculation. So this is an oversimplification of the climate system, but you can see basically an element of it. So let's say you're down here on the Earth and you want to push back 2.2 watts because there's 2.2 watts of extra uh, energy being pushed at you because of the forcing from above. So if you're Earth, so you increase radiation by 2 watts, or you want to increase radiation from 398 to 400. So basically, we can just go to the equation here. You remember it's proportional. T to the fourth is proportional to the radiation or the forcing. So basically, you just go ahead and you take 400.2 watts divided by 398 watts, take the fourth root, and see how much the temperature changed. From 288, it went to 288.4. So the ground has to warm here by 0.4 degrees Celsius to push up an extra 2 watts. Now, of course, warming today is generally thought to be a multiple of that, something like 1.2. So what's up? Well, from the diagram, I think you can guess some of this because the system is much more complex, even more than what the diagram suggests. So first, there are three components, I think, that amplify the effect most dramatically. The first is what you can see right here. The atmosphere pushes back on the radiation. So when you radiate extra, it pushes back extra. So it's kind of a feedback loop. And obviously the mathematicians can do calculations on that, but it's a very definable feedback loop. And it means you got to push harder. So you got to push like more than 2 watts to get 2 watts out. That's presumably obvious to you. The second is that water vapor is a strong greenhouse gas. And you'll remember from engineering class that warmer air holds more water vapor at a given humidity, and relative humidity is expected to stay roughly constant in a warmer world. So we get a lot more water vapor in the atmosphere for each increment of temperature rise. So this creates extra temperature rise. Methane levels have also risen, and methane is an important greenhouse gas, as I'll show you later. At the same time, two things have cooled us. The first is that aerosols from sulfur dioxide pollution have reflected extra sunlight to space. So of this sunlight that's kind of coming down, there's extra, this 100, included in that, there's been an enhancement from aerosols, high elevation aerosols that are making the Earth just look a little tiny bit brighter. So it's a little over a watt, and so that's cooling. So that impacts the math. And secondly, the oceans are absorbing energy. So you're not you're not pushing out 2.2 watts. You're pushing out less than that because some of it's warming the Earth, in particular the oceans. So that's sort of the pushes and pulls. If you're trying to build a model, that's the kinds of things that you build in your model. So we can make this simpler, a lot simpler. And here's how we can do it as engineers. There's a term called climate sensitivity. And what's helpful here is if you think about the radiation equation, the one I showed you earlier, I've got a plot of it on the right. Note that forcing changes are really small compared to the overall radiation. Remember, I kind of talked about it's like 1%. So a linear equation works really fine. You know, I've just got an asymptotic dotted red line against that equation. So that means you can kind of take the shortcut, and you can say that temperature change varies directly with the changes in forcing. Because again, this is fundamentally a radiation problem. And so, you know, there's a constant in that relationship, the slope of the line, and that slope or constant is called climate sensitivity. This climate sensitivity is kind of fundamental to climate science, and climate scientists use it to benchmark their much more complex simulations. So if one of them does a forecast and another one does a forecast, if they want to get together and say, well, is your forecast showing higher temperatures or lower than mine? What they would typically do is they would say, okay, at 2 times CO2 level, so that's similar to that 600 number you saw earlier, 600 parts per million. What temperature does your model say? And then they back calculate that constant, and they basically compare that constant in one model versus the constant in the other, and that's how they benchmark the forecasts. And so let's talk about the benchmarks and how we can use those benchmarks. Well, you know, you give engineers a straight line, we can run with it. So here are the benchmarks. And it depends on what kind of model they're running. So if they're running a model that's a transient warming sensitivity, so it's kind of in real time as CO2 is ramping up, how is temperature ramping up over a kind of shorter term? So this is kind of over decades periods. That's short term in climate. Things don't happen instantly. They find that constant or coefficient is about 0.49. So it's 0.49 times the forcing from CO2 alone. There's forcing from other gases, but if you reference it to the CO2 portion, you multiply CO2 forcing times 0.49, you get the global average surface temperature change with everything taken into account. And that's how they would benchmark their forecasts. And we can use that. At the same time, there's something called equilibrium warming sensitivity, and that's over much longer time periods, century or centuries. In particular, that's when the oceans have had time to fundamentally catch up with the temperatures, not just the top layer, but kind of a little bit of the deeper layers as well. So there's less heat flux going into the ocean. Because there's less heat flux going into the ocean, Earth has to be warmer to radiate that extra energy, try to restore equilibrium. So those models, they use a coefficient of around 0.81. The midpoint between these two coefficients is an excellent rule of thumb for eyeballing our future, in my opinion. I found it to be really handy. If you use the equation from a few slides ago, you'll remember that forcing is 5.35 times the log of the concentration ratio. So you can actually substitute that right in here. So if you've got the equation here, delta T equals 0.65 times the forcing, and then you plug in the forcing, this other one of the 5.35 equation, boom, delta T equals 3.5 times the log of the concentration ratio. This is a crazy handy formula. It's not perfect, but it gets you in the ballpark. In fact, in my opinion, it works great. For example, I've got an image on the right, and what I'm graphing here is ppm on the x-axis versus global average surface temperature warming, as calculated by the IPCC and this quick and dirty equation. The IPCC has like 5 formal cases in the last edition, and at kind of the end of their forecast period, this is where I've got a dot there where their CO2 level sits and where their global average surface warming sits. And the orange line is the one you get from that little equation. And it lines up really well. So basically, I've just done a super simple calculation, and you kind of get more or less where they got. And part of that is because the coefficients we've used are fundamentally from the work that they did in those simulations. So you won't find this calculation in a book, but in my opinion, it's sound. If you want to get fancy and you want to know what the temperature is kind of in the middle of like an aggressive ramp, you can just modify the equation and use the 0.49 instead of the 0.65, and then you'll calculate kind of the lower black dotted line. Or if you kind of want to know, okay, what if we waited a couple of centuries, what kind of temperature we're at? Well, I don't want to use that orange equation. Well, then you can use the 0.81 and come up with your equation here, and you'll be more up to the upper line. Hopefully, engineers can use this approach and not feel powerless. You know, we don't have the simulation tools that the PhD researchers do. But I feel that engineers want to be able to calculate things so that they can feel and believe them and understand the push and pull. I think there's an equation. There's an expression: give an engineer an equation, and you can watch them reinvent the world. So here you have your equation. So this is the end of the difficult theory. There's a little bit more theory in this deck, but it's very easy compared to this. So hopefully you're still with me. The rest of this presentation talks about the implications, uncertainties, and context around all this. So there's three things with this equation right off the bat. And the first is obviously it's a logarithmic equation with diminishing impact over time. So what does that mean for us? So here's a blow up of what you get with warming for that equation. So you read the warming on the right hand side of the scale with the orange line. The blue bars is the slope of the orange line. It's the temperature rise per 100 ppm of CO2 rise. Notice how the impact of the CO2 becomes less as we move to the right. It's good. It's very good. We don't have the same slope as we did coming out of the Ice Age bottoms. As CO2 levels rise, you can see just right over here. CO2 levels rise, you can see clearly that has a diminishing impact, but unfortunately still very much of a thing going forward. If you want to get a little bit more detail and think about this, you kind of see this cooling here at the bottom of the ice age, and you kind of go, well, the ice ages were cooler than that. It's true. So even though these numbers here are really big coming out of the ice ages, like over 2 degrees Celsius per 100 ppm, effect was even more because remember that tipping about the ice sheets. So you had extra forcing beyond the extra effects, beyond just the CO2 forcing in the atmosphere. Um, so that's why, fortunately, the slope isn't more than it is. If we'd used that same sensitivity, this sensitivity, or even the one that includes the loss of ice, the climate scientists would be imagining that the Earth is just going to be cooking up. But that's not what they're forecasting. They're forecasting this diminishing return, kind of more muted line. So hopefully that gives you some context. And too bad that log phenomenon doesn't mean the whole thing goes away. It's still a problem. It's just not as bad as it would be. So I'd like to do two examples just so you can see how easy it is to do a climate calculation. Um, I'm not going to go through every line here, but you can pause if you want and go through it. It's just basically very simple algebra. The first is let's take a scenario where we'll use the rule of thumb formula and do an example where what happens, how much warmer will the planet Earth be in 50 years if we keep emitting 41 gigatons per year? So what you do is first you just do that material balance that we did right kind of near the front of the presentation here. And don't forget to take out plants and oceans absorbing about 45%. And so what you find after 50 years at 41 gigatons a year, the ppm of the atmosphere goes from 420 to 563 parts per million. So you plug it into the handy dandy formula. So you get global average surface temperatures that are 2.5 degrees Celsius warmer than pre-industrial. So that is 1.1 degrees Celsius warmer than what you'd get with this equation at today's warming condition, if that was halfway between the equilibrium and the transient line. So this is global average surface warming. I'll talk more later on kind of the nuances around where you live, but maybe where you live is kind of somewhere in the middle of North America on land, and land temperatures are warming faster, and the big oceans are warming a little bit more slowly, which probably seems obvious to you. The specific heat of the ocean is, enormous. So land temperatures are leading in a lot of places by about 50%. So you take this 1.1 and probably add 50%. Let's do another example here. To put, for example, if you live in the United States, we think we're really big with our emissions, and we are. The huge emissions. So how much will USA, the entire country CO2 emissions alone, how much additional warming will they cause over the next 50 years? So if you do kind of the same material balance, you see that the CO2 levels on Earth get to 546 instead of 563. So this is with not only all the planes, trains, and automobiles, but it's all the industrial energy, it's all the heating, it's all the power plants, it's everything. So if you put that into the handy dandy equation, you get 2.4 degrees Celsius instead of 2.5. So the planet will be 0.1 degrees Celsius less warm after 50 years. So the land impact would probably be 50% greater, so 0.15 degrees Celsius. That's not a typo. That's what it is. Let's talk about confidence intervals, because if you're a good engineer right now, you're thinking, okay, what's the confidence intervals? How good are these numbers? kind of rely on them. Um, so much of what the IPCC does is when they get together, they get like several thousand climate scientists together at these regular intervals to basically have massive numbers of peer reviews, and they analyze, discuss, and debate each other's methods, data, analysis. And coming out of all of that, they spend a lot of time on uncertainty ranges. And they use um, probability ranges. I'm used to them from the oil and gas business. But for example, P5 to P95, that means probability. So between 90, the P95 and the P5, there's basically 90% chance that the data will fall within a certain range. And they show you what that range is. And you see that here. Um, and that's from the climate sensitivity values. So basically, it's when I look at this, I look at it and I say, yeah, the number is good, about plus or minus one third. So to me, I think it's inappropriate to just use that equation when it's not precise. It's so imprecise. I think you should always remember and always say it's plus or minus a third. All right, let's just talk about some other theory now, other greenhouse gases. So first of all, the big kahuna, water vapor, um, we don't consider it in climate books and in this slide deck. Um, they don't talk about water vapors being a greenhouse gas. It is absolutely a greenhouse gas, but the convention uh, is that you think of it as a feedback. And why is that? Well, because as climate changes the atmosphere, water vapor goes up. So it's obviously a feedback. A number that's on the slide, you should remember, it goes up about 7% per degree Celsius or 4% per degree Fahrenheit. Um, but it's a feedback effect. The amount of water in the atmosphere goes way up and way down, way up and way down every day. It's weather. It's not like the other gases that kind of follow these curves, these behaviors. Water vapor is all over the place. And it's what keeps climate scientists employed because it's the biggest uncertainty, and you'll understand that more. Um, one fascinating fact to put this in context for you, I've read that the average atmospheric molecule of water only stays in the sky for about 7 days. The water cycle is amazing. So let's talk about other gases. So here's uh, a well-studied, talked about slide that the IPCC puts together. And that's the climate forcing of not just carbon dioxide, but other gases. And so on the bottom, you see watts per square meter because you're now climate scientists. Um, you see, and you know what that means. And so for carbon dioxide, there's your 2 watts per square meter at about 2019. And here you see a bunch of other gases. Probably the second most important would be methane, which you read and hear a lot about. And there's a component from the methane itself, but methane is also a catalyst for ground level ozone, which is also a powerful greenhouse gas. So you put those two together and you see that methane's contributing over a watt. So ozone levels are more thought of as a feedback. So that's why it's not kind of shown as a gas here. Um, but it shows on top of the methane, or it shows on top of some of these other gases that have an impact on it. And then another one I think I want to, your eye probably went to it, you've got sulfur dioxide. So it's cooling. I talked earlier about that energy balance of the earth, and those aerosols are reflecting sunlight back to the sky. So let's talk a little bit about potency. How do people choose to think about these other gases? There's three things. If you're another gas and you're wondering how important that gas is, the first thing is, does it filter or absorb um, radiation at a frequency that's not already completely filtered by carbon dioxide and water? Remember how there's some sort of holes in the spectrum where the long wave radiation is getting through? does it does it operate at that window? Um, if it doesn't, it's not important. Um, the second is how much of the gas is already there. If there's a lot of that gas there and you add a little bit, it doesn't matter much. If there's none or almost none and you add some, it tends to have a much larger impact. And how long does it last in the atmosphere? There's some gases that last for centuries, and there's some gases that only last for days. So the ones that last for centuries, they're much more potent. That makes sense. So there's a kind of a shortcut way that people talk about. You've probably read about this if you've been even slightly engaged in climate science, and it's called global warming potential for different gases. And the reference point is if you think of CO2 as having a potential of one, how do other gases compare? And so here's a table that I think gives you a sense of how that calculation works. So here's kind of methane and some other gases. And you see that the mean lifetime is quite different between these gases. And the radiative efficiency is also quite different. So, for example, CFCs, they're in the atmosphere about half as long as CO2, but they are much more powerful. And so if you put the lifespan and the potency together, um, and you've got curves on how quickly they disappear out of the atmosphere, you get these 20-year and 100-year GWP values, if that makes sense. So that's if you get 1 mole of one gas versus 1 mole of the other gas, how much more of an impact does it have? So that's that. Um, so let's do a simplified warming comparison, just a little bit of math here, and let's compare the leverage we get from reducing methane versus the leverage from reducing carbon dioxide. So we're cow here. I'm kind of blaming the cow, but there's a lot of different things that release methane. Oil and gas operations um, sometimes release methane, and that's got a lot better. I know that a lot of the farming activity, particularly cattle, emit methane, and then some other agricultural processes emit methane, and everybody's trying to do better, right? So notice that methane. So this is the amount left in the atmosphere versus time of a mole of methane dropping very quickly versus a mole of carbon dioxide dropping very slowly. So after 100 years, there's still about 40% of the CO2, still in the atmosphere, whereas the methane's virtually gone. So let's just do a calculation with that. So using our watts per square meter knowledge, so today we have methane forcing about 1.1, CO2 forcing about 2.2. So how much are those things warming the Earth? You've got the methane is warming at about 0.54 degrees Celsius, and the CO2 a little bit over 1 degree Celsius. If we suddenly eliminated all the methane, so in this column, what would happen? So you just take the attenuation curve and you reduce the forcing. This is how much that extra warming would go away. And you do the same thing with the carbon dioxide, you can see how much the CO2 warming would go away. So in 100 years, notice that you lose all that warming from the methane, but you still only lost some of the warming with the CO2. So you kind of see the tremendous leverage we get from reducing methane. And, it's not easy to reduce anything. People are not trying to emit these things, obviously. Um, but the CO2 emissions are so very large compared to the methane emissions. It shows you why there's so many eyes on the ball with respect to methane. This is a fairly simplified calculation that I've done here. And these equations are meant to do slightly different things, but I think this gets you kind of in the ballpark of kind of seeing the comparative importance. Let's have a little fun with the timeline of how pollution has kept us cool. Homer's looking a little bit angry here because he's thinking, how can climate science be so complicated? Um, I think this is a very underpublished story. Um, so in this graph here, the IPCC has done their best to make a consensus reconstruction of the forcing effects by gas, along with total forcing. So it's like it's the tornado chart you saw before at 2019, but it's how that's changed, how that tornado has evolved with time. So the combined number is the black line. So here is the 2.2 where we're kind of sit today. And then the CO2 forcing is the orange line going up. And then the other lines are all kinds of other things. Um, Notice the gray line that has a big uncertainty range on it. Um, what this is, again, this is the sulfur dioxide. Um, the aerosols from the sulfur dioxide are creating a sunshade and they're reflecting a little bit more than 1 watt per square meter back to space. Um, the sulfur dioxide is primarily from, the so-called dirty coal, and there's a lot less, plants running dirty coal or they're cleaning up their sulfur dioxide. And so that's why you can see that the number is moving back up, like it's becoming smaller. Also from, bunker oil, the high sulfur oil, which is generally no longer used in the shipping, but it was quite common. So we've cleaned up acid rain by reducing sulfur dioxide, but we've also lost a little bit of the sun umbrella that was kind of keeping us cool. So again, that's why Homer's a little bit angry. This is confusing. Um, if you hear about people that are working on geoengineering the atmosphere, what they're talking about is adding aerosols to the upper atmosphere, but some benign aerosols that don't cause acid rain. I know a lot of entrepreneurs are looking at stuff like that. Um, let's talk about some other climate drivers, which are completely and totally super important. The first one is clouds. Clouds are definitely number one. Um, Cloud cover is the main contributor to uncertainty in climate models. Um, Lower altitude clouds are cooling. So, if it's really dark outside and there's a, big dark cloud over top of you, it's dark because that top of that cloud, if you're flying in a plane over top, it's bright white. And the sunlight's kind of going back to space. Lower, high altitude clouds like cirrus clouds, they tend to be ice crystals, and the sunlight kind of is able to get through them to the ground, but they're effective at trapping long wave radiation. So they're quite warming. So the IPCC spends tons of time on this. And now Homer is a little bit overwhelmed here because he is not a climate PhD. But a lot of the IPCC report, and I'll talk about the report later, they talk about working on studying cloud types. And here I show the main cloud types that they're working now. So this is a graph I've done where I just capture their expected forcing ranges, the amount of forcing change you would tend to get for every 1 degree Celsius of temperature warming. And so you see that some things tend to be cooling, like this one, tropical high cloud behavior, and some tends to be warming. So if you want to be a climate critic, this is one of the key places to look. This is the IPCC values shown here are the P5, P95. So they're 90% sure the values lie in this range. When you put these together probabilistically, you get a range from where the clouds could be cooling slightly or kind of significantly warming. And most of the models tend to be kind of around the central values here. And there's a small chance it could be outside of these ranges. Again, there's a long section in the IPCC, and the scientists are able to watch it very closely. Satellite monitoring is obviously a game changer. Basically, you can you can look at how bright the Earth is. It's called the albedo number on the Earth. And so you know how many watts you can see with your eyes are going in, and you measure the watts coming back out, um, that's reflecting visible light. And that's largely driven by what's happening with clouds from one day to another, and to some extent snow and ice, um, things like that. But the big E here is clouds. Um, let's jump into a few others that are a lot less important, but still significant. One is volcanic, call it pollution. So not the carbon dioxide, the life-giving carbon dioxide that volcanoes give us, but they also can contribute to, acid rain. They put sulfur dioxide in the atmosphere, which is that aerosol thing we talked about before. It's just the same as the coal plants. So this plot has a blue line, and it shows the forcing effect of volcanic aerosols over over the last long time period. Um, so it can be as much as 3 watts per square meter, but it doesn't last. So right after a big volcanic eruption, basically the effect of that is greater than the climate forcing from CO2 at the moment. But again, it doesn't last. Typically, if a few months after the eruption, it's generally gone. The pace of future eruptions is an example of one of the things that climate modelers have to put in to their future scenarios. So and they do. They will predict a pace of volcanic activity because it does impact the models. You can see here there was a period of time from kind of 1960 to a little after 1990 where it was always most of the time there was a fair number of volcanic aerosols. So this has been kind of a helpful thing. Unfortunately, volcanoes have been fairly quiet. Like I say, fortunately, from an aerosol cooling perspective, the volcanoes have been a lot quiet for the last about 30 years compared to the longer period before that. Sunspots come up a fair bit. Um, I think if you spend a little bit of time on here, you'll see that they're not as important as you might think. First of all, here they're very predictable, or they have been for the last 50 years. Here you see, again, this is something that you can totally measure from a satellite super accurately. Um, so this is coming in from a sunbeam. You got 1360 watts per square meter. It's going up and down, up and down. There's kind of like a 10-year cycle, and that's about 1 watts per square meter. So this is something it's obviously in the climate models. They'll continue to uh, either put in the average, or if it's a detailed model, which I'm sure most of them have, would have this cycle kind of going on and going forward. It's less than you would think. So at first you kind of go, 1 watt? Well, that sounds like quite a bit compared to the forcing of 2.2. Again, this is the sunbeam. And when we're talking about like 2.2 watts, that's day and night, poles to equator, all the way around the world. So if you actually do that math, 1 watts per square meter works out to 0.18 watts per square meter of Earth, 365. And if you want to go through the math I've got in the top right box here, you can pause, and it's just grade 7, 8 trigonometry. Now there was a period where the sun was more quiet. And so you see it here in kind of the 1600s. Again, in watts, after you do this 0.18 factor, it doesn't matter much. It probably significant, but it's still pretty small in the big scheme of things. I don't know if you can totally see the scale here, but the scale goes from 1362 to 1360. So there you've got like 1 or 2 watts during this little ice age kind of period. So I think it's important, but it's not as big as some of the other changes that are going on. And it's obviously something that we need to keep an eye on with the satellites, and we and they do. let's talk about orbital variation. So I introduced orbital cycles in the Ice Age discussion earlier. These do not impact the annual watts hitting the Earth. So, if it's a round circle or an ellipse, it's generally about the same number of watts, but it sure does drive the seasonality on the planet. Um, and so this is calculated a long time ago by this gentleman here. Um, and I think he did it under very difficult personal circumstances. If you want to have some fun, you can read about when he calculated all this stuff. Um, but he did, and he was able to come up with this line. And what this line is, it's not how strong the sun is, it's how basically how strong the sun is at 65 degrees north, where a lot of ice changes happen on the planet. It's kind of where the most uh, differential activity in more brightness or less brightness happens based on what's happening with sea ice, things like that. And so you can see in this graph, you can see right now where this is point zero, and you can see 150,000 years ago. And they've shaded the areas where you're in an ice age, and in white is where you're not in an ice age. So this is the last interglacial period shown here. And you can see that it started, um, or there's this big high and this big low, kind of a big swing. And this tends to generally conform if you go back, because they can calculate this big swing here tends to conform with the ice ages starting or ending. Um, and here we are in our present interglacial period. And this would be about the time that an ice age would typically start again, 100,000 years, and we've been interglacial, but it's not. I think we have enough CO2 in the atmosphere that it's probably not going to happen. Um, Maybe almost certainly, who knows? Um, and it's sort of we're going through an unremarkable period of swings in what they call insulation. So don't hold your breath on this being a savior or a devil kind of going forward. And let's just highlight nature. I don't think we talk about nature enough when we talk about climate science, because it's so central. So plants are superheroes. No way around it. Here is the blown up data from Mauna Loa. In northern hemisphere, there's way more land than in the southern hemisphere, um, where there's plants, and that's why there's this big cycle. And there's not one kind of an opposite one when it's summer in the southern hemisphere. So you get this big drop, 2 month drop, um, from 419 to 414 every year. How can plants be so amazing? Well, because there's a lot of them. Just a reminder, there's a picture from NOAA has this leaf index. Um, and I'll talk about the leaf index later. But there's a lot of plants, and the extra CO2 is helping the plants grow, and they're doing great. But maybe I will say now that what this leaf index is, it's really changed by looking at the spectrum of the light coming from Earth. By the amount of green that's coming up, they can get a sense of what's the leaf area of Earth, and it's been going up by a lot, and it's conforming with the sequestration numbers I showed you earlier that talked about plants absorbing carbon dioxide. And they're doing a lot of it in the summer when there's this big drop, right? Um, why is CO2 helping? I'll talk about that later. But maybe right now I'll talk about why does CO2 have such a long life, half-life? Remember we saw earlier, like there's still 40% in 100 years. Well, plants absorb the carbon dioxide in the atmosphere very rapidly, but they don't destroy it. So it's very different than methane, which is kind of naturally destroyed in the atmosphere through natural processes. So most of the CO2 is released back into the air when the plants rot, when the leaves and stems die and rot. Some stays in the soil, And as CO2 levels rise, this whole cycle gets bigger. Um, and as the plant cycle gets bigger, it holds more CO2. So it's a super helpful and dynamic cycle. Yay, plants. So let's do math on that, or at least show you some gigatons again. Um, this picture here, cartoon, is not in gigatons of CO2 because remember we talked about 41 gigatons a year. So now we're just talking about carbon, gigatons of the carbon molecule itself. So it's a smaller number. So for example, fossil fuels are putting up almost 10 gigatons a year of carbon. Plants every year are taking in about 100 to 120 gigatons. Um, and then they're breathing it out and they're decaying. So the plant cycle is 10 times larger than our fossil fuel emission rate. So that's why those Mauna Loa CO2 numbers are. The ocean cycle is also 10 times larger. Um, if you're a CO2 molecule and you're floating around the atmosphere, you'll probably be sucked up by a plant or an ocean in about 5 years. So, water, I talked about 7 days, CO2, it's about 5 years, but most of it ends up getting re-released. So that's why you get the long cycle time on the CO2. So climate models obviously include this. It's fundamental to models. I want to talk a little bit about deforestation here, called human land use. So earlier we talked about the 41 gigatons, and a lot of it's from the fossil fuels. So that's the difference between the green line and the orange line. Um, but there's also this lower line, which is generally called land use or something like that. Um, the idea here is that when you remove a forest, the carbon goes into the atmosphere and the farm crops rot much faster than wood forests rot. If that makes sense to you. Wood is much more stable than farm waste as far as breaking down. And so wood forests are a better carbon sink than shorter cycle farm activities. Notice how farming was a bigger deal. Um, I guess you can't really see it here, but it was bigger than coal until about 1960. Um, also notice how it's been trending down a little bit. Um, so, recently, while fossil fuels have been trending up slightly, the overall number has been pretty close to flat, and that's been aided by reduction in the rate of the deforestation. So if you hear about projects like taking carbon offset credits, things like that, they're working on moving this green line further down. So I told you that the IPCC models all this. Um, Here is the historical values that they back calculate. So remember, I calculated the 0.5 when I did it myself, and I encourage you to go ahead and do it. You'll get a similar number, but they do it with every year. So every year you see the human caused emissions in gigatons and how much is going into the atmosphere. And below it, you can see how much is going into the land and the oceans. And you can see their percent number. It's about 45%. So I think that's pretty cool. So let's talk a little bit about the IPCC, because I think it's very important for you to know what they do. So every 6 years, they get together, they do all the things, have all the meetings, and they come up with this document which does the best job that they can do to capture what's going on. There are three reports. The physical science report is the one I think is relevant to this talk, and it's the one I recommend you download if you're interested. It's a couple thousand pages. If you read it, do not spend time on the upfront summary chapters, in my mind. You can read them, but I think the meat is in the working group chapters. I feel like the upfront summary chapters were written by people that were constrained by political pressure or influences, but the individual working group chapters, they do a great job of documenting the concept. talking about where they as scientists struggled, where they had consensus, and why the variables have the uncertainty that they do. To me, they sounded like scientists, not like politicians. If you do read it, the climate jargon can be difficult, but if you have Wikipedia running on the side, for example, I think you can get there. It's also helpful if you have some basic knowledge of weather, but that's obviously very available and easy to get. And I bet a lot of you know a lot of the science from school. Okay, so IPC scenarios are by far the most visible set of assumptions. Um, in the current report, there are 5 emission scenarios that drive the forecast. You all know what goes in determines what goes out, right? So the left plot is of CO2 emissions in gigatons per year for the 5 forecasts. Recall that we've been at roughly 45 gigatons per year the last dozen years. Um, so when this graph was made, um, there's been some more kind of flat periods here. If the black line continued a little bit longer. But a lot of science for this report was done around 2020. Now the upper forecast jumps from about 40 gigatons per year, 41, to over 125 gigatons in about 50 years. This case is labeled, they call it the 8.5 case because that's the CO2 forcing in that case. So 8.5 watts per square meter versus 2.2 watts per square meter today. So in my mind, hopefully that's more of an academic what if case. If you read about fire and brimstone coming in the next few decades, it's likely that the person that wrote about that was referring to discussion around this scenario here. The lower light blue case is a net zero by 2050 case, which then goes negative beyond that. This is, of course, the aspirational case. This is the goal of much of the current climate narrative, and is to prevent us from exceeding 1.5 degrees Celsius warming. This case is called 1.9 because the forcing is reduced from 2.2 to 1.9 by the end of the forecast period because we actually have negative emissions going on in that case because of carbon sequestration processes and things like that. So in the rest of this presentation, I'm going to show a lot of forecast numbers relating to the orange case. It has emissions staying roughly flat for about 30 years and then declining. I'm in engineering and I like to fit trends. So I'm fitting the current trend. That's all I'm doing. No offense to the people trying to get to net zero by 2050 or people that are worried that we're going to just go back to extremely high increases. I'm just following the current trend. So it has forcing growing to about 4.5 watts per square meter by the end of the forecast period. So about double today's level. And you can see the cumulative ppms on this middle graph. All right. And just, sorry, I was covering this graph, but I'm just tying to the 45. So let's talk about what those forecasts say. First of all, we talked a lot about nature. And so those forecasts actually, they're transparent about what they assume on those sinks. And they're forecasting those sinks will continue to be very helpful. So for example, the ocean in all these scenarios, this one doesn't have the lowest forecast, the light blue forecast from the previous graph, but has the other 4. And you can see all these forecasts, the oceans continuing to absorb carbon dioxide and net lands are continuing to absorb carbon dioxide in a helpful way. And at the bottom is a fun picture and it's showing how much work, where the Earth is doing all this good absorbing of CO2. And you can see kind of the northern latitudes here. The more green it is, the more carbon is being captured by the Earth. And there you can see it's going on. So that's a cool IPCC image. Let's talk about model uncertainties. I told you that the IPCC takes confidence intervals very seriously. If you read the book, or the document, you'll certainly find out about that because they talk about it extensively. What I've done here, and you won't find this diagram in the IPCC, but I've basically digitized various tables and things to put this together, so it's all in one place. Here's all the hair on the science in one place. So in orange is the P5 to 95 confidence interval for each forcing or feedback. So here's the forcing components, and here's nature's response, which creates secondary forcing. So there's CO2. So it's ranging from like 1.9 to about 2.35 or 2.4 with a P5, P95 confidence interval at 2019 conditions. And here are a bunch of other influences. There's amazing detail. There's even things like the condensation behind airplane jets. um, there's all kinds of things that are in their uncertainty ranges. There's volcanic activity. You can look at it at your leisure. Um, I put red diamonds besides those items that have the widest confidence intervals or the greatest uncertainty, depending how you look at it. So the key ones are ozone, aerosols, sea and snow ice cover, and clouds. So if you put this together, you can see the combined uncertainty ranges of the pieces. And this is basically where the plus or minus one third comes from that I talked about earlier. So hopefully that makes sense to you. So if you want to be a critic, go after those diamonds. Um, so temperature forecasts. Um, let's talk about those and put them in context. Um, I think we're done in the theory on warming. Um, so climate projections reference 1850 to 1900 as a starting point. Um, the IPCC does a good job of kind of providing some historical data. Um, and so here you see kind of the last couple of thousand years, and you can see that it was actually a little bit of a warm period that we started, where these forecasts are benchmarked to. So it kind of sits right about here. That's why the zero this is the reference point. Um, if we use it since year 600, the warming number that's quoted in media would be less, but it would still be the same temperature. So I think it's arbitrary a little bit where it started, and this is the reference point that they're using and why they chose it. For what that's worth. I don't think it matters, but it's interesting. So here is one of the key visuals from the IPCC, which summarizes, move myself out of the way again, temperature forecasts by scenario. Remember, we talked about those scenarios earlier. The shading is for the P95, P5 uncertainty ranges for a couple of the forecasts. So for the 7.0 case, there's shading. And there's also shading for the 2.6 case. So this is kind of the plus or minus a third. The orange forecast, which doesn't have shading, is the one that is status quo emissions to about 2050. And these values, again, are global mean surface temperatures, oceans, and land. I think this is great, but to me, I have a hard time relating to this. What does it mean to me? What does it mean to the plants in my yard? Whatever. So let's think about some of the complexity and nuances about temperature. IPCC, something that they have charts that kind of show how temperature changes depending on where you're located. In general, first of all, land temperatures are warming faster, so they're leading. Ocean temperatures are warming more slowly, they're lagging. So if you take the global average surface temperature and you multiply it by 1.5, that factor works for much of USA and Canada, Europe, and Central South America. And a factor of 1.1 works for much of India, Australia, and Central America. It really depends on how, the really, really large continental land masses have the least ocean influence, and so they're cooled less by the inertial effect of the ocean taking its time to warm up. So let's make this tangible. I've digitized the IPCC curves, converted them to degrees Fahrenheit, and multiplied by 1.5. Um, so notice, please, two benchmarks that I've called out from this graph using the orange line. So from kind of 1950 to today, we have about 2.6 degree Fahrenheit warming. I really like comparing things to 1950 because in the US, the National Weather Service has great data from 1950 on for so much of the country. And so we can actually look and get a feel for whether or not these forecasts seem to be conforming, or this analysis seems to be conforming to actuals. And so 2.6 warming to today and 1.9 warming to 2050. So in about 25 years from now, 26 years from now, how warm might we be, plus or minus a third? Um, so the first thing I'll do is I will show you Denver data in the context of the 2.6 and the 1.9. So here's a 2.6 Fahrenheit bar, and I just kind of stuck it next to Denver historical annual average temperature degree Fahrenheit. So day and night, 365 days a year. Each year, you've got some years warmer, some years cooler. And, they generally plus or minus a couple of degrees Fahrenheit. Um, and so I put the bottom of the black bar, where maybe ish it was um, in the first couple of decades of this time period. And the top one sort of looks like where we were in the last 10 years ish. Um, so yeah, maybe it sort of lines up. And then for reference, I put the 1.9 on top. And so this is in 25, 30 years. Here's where the average day would be. So the blue dots would kind of average up here. So they would average about the same as this kind of warmer than average year in 1980 and warmer than average year in 2012-ish, whenever that was. I've also looked at summer temperatures because we feel the heat more in the summer, I guess in a negative way. Um, and it sort of looks similar. Um, with big cities, you always worry about the urban heat effect distorting it. So I've kind of done this again on this graph here, where I just went around the country, and you can do this too. I encourage you to do it actually. If you go to the National Weather Service, just type in National Weather Service, hit enter, go to the first thing that pops up. It's their homepage, and they have a button called Past Weather. And you just go anywhere in the country and you can call out their past weather. And they also have labeled each of their weather districts. They have like their nameplate weather station. And I think it's pretty cool especially if the nameplate weather station isn't a big city, you can get pretty good data that probably isn't distorted um, by the urban heat effect. So I've done that here. I kind of went around the country and arbitrarily grabbed 9 towns. And I've done this with other towns too to see if it changes it. And it doesn't materially, but do it yourself, especially do where you live or where your vacation house is or something. Um, and so here are kind of 9 places in the US, and it's average annual data, and all of them kind of have noise. And maybe some of them you see the trend, some of them you don't. But if you average them and you put them all together, here you can see that it's going up by about 2.6. It looks reasonable. Doesn't look that bad. Um, looks like the estimate could make sense. All right. Just real quick, I'm going to close the window here. There's somebody mowing the lawn outside the window. There we go. Apologize for that. Okay. So let's jump ahead and talk about something here. If you look at the 9 city average, you might notice that maybe it looks like a lot of the warming has happened, particularly these last data points in the last 10 years. I think it might be partly explained by the overall physics. So remember the slide I showed you about how the IPCC does the warming by component. You can see that the net forcing was really pretty darn small, um, and just really started ramping up a lot very recently. And a lot of that's because we stopped having this increasing amount of sulfur dioxide emissions, so help from the aerosols, and especially lately where we've had a reduction in the amount of SO2. So solving acid rain problem, I think that gave us a bit of a kick. Maybe I'm reading too much in the data, but I've seen this in a lot of plots where, the last 10 years looks like it's warming up more than you would think, especially when you think that we've been emitting, the Industrial Revolution, that was a long time ago. We've been emitting a lot of stuff. But we seem to be getting more of a kick right now. And I think that's the math. So that's a kind of a climate nuance that I don't think you're going to read in the newspaper, but I think it's pretty real. Um, if you plot Alaska, I like to go fishing. Um, you see that it's warming a little more. Um, Climate science, they talk a lot about Arctic amplification, but it's what's expected, and it does look visible in the data. So, I'll leave it to you to go ahead and do that if you want to kind of study that. And the IPCC has a map, if you're interested, that tries to do this. Instead of just using the 1.5 factor, you can do it with a lot of detail here, which is trying to show that kind of the current trend at 2018, how much warming is there. And the increased color shows where there's more warming. Um, and so there you have it. They've also called out for big cities how much of the warming is due to urban effects versus how much is due to climate change. So you got a place like Los Angeles where it's generally driven by the fundamental climate physics, and you've got other places, Athens, um, for example, Iran, where the urban heat effect is dominating the number. I talked a lot about the 1.9. I should just point out that that's till 2030. Um, Certainly, our kids are going to be around a heck of a lot longer than that, right? So that case has us going up to 2100 at year 2100 by about 4 degree Fahrenheit. Um, so I think that's important context for you to keep in mind. So some people may think that the IPCC changes their mind a lot, and certainly their work processes are improving a lot. They're getting a lot more data. They're doing a lot more things. Um, so remember, I talked about that basic equation. For example, there's the delta T equals 0.81 times the forcing from CO2 to get equilibrium, temperature change, long run. So this is for each one of these is 6 years apart. And this is what the IPCC formally published for their uncertainty ranges for that equation at 2 times CO2. So at double so at a little bit less than 600 parts per million CO2, they said 1.5 to 4. And then 6 years later, the same range, and it's changed a little bit, but it hasn't changed a lot. Currently their best estimate, official best estimate is 3.0 degrees Celsius, or 3 degrees, maybe you shouldn't have that extra decimal there, but 3 degrees. So fundamentally, it's still the same story. What I think that speaks to is that the fundamental physics aren't that hard, even though it can be made incredibly complicated and nuanced. Um, it fundamentally hasn't changed for that reason. So let's try to put the temperature in context with our lives. Um, I think this is pretty important, which is kind of using daily data. Can you tell? So, before I was showing you annual data where things would change by, 1 or 2 degrees. What happens on a daily basis? And I say here, don't be surprised if you haven't noticed the change. So I'll start with Denver. So what I've plotted here is July. So July 1st, the daily high in July for Denver for the 30 days in 1950, and then the 30 days in 1951 and 52. So there's 5 years of July days in the 50s. So, there was a few really cool days and a few kind of really hot days. Um, and here it is from 20 to 24. And on the right, I've got the bar. I've got that little short bar there. Sorry, I've got a camera in the way. I've got that short bar that shows 2.6 degrees Fahrenheit. And then I've got a bigger arrow, which is kind of what the temperature range. And if you look at that, you can see that the daily weather variability is about 10 times more um, than the daily shift. Um, so, if you wake up in the morning and it's a hot day, yeah, climate has probably influenced it a bit, but it's a hot day because it's a hot day. Um, Here's the same plot for Houston. Um, so I think it's somewhat more noticeable for Houston. I think it would still be hard to feel. The daily variability there is about 8 times the climate shift. Um, so a climate scientist would want me to point out that just because the signal to noise is really small doesn't mean there's no signal. There's a signal here, and you can tell it when you plot, the annualized data. Like in the top right here, I've kind of got the annualized data. And yeah, maybe it looks like, there is or there could be a shift there for Houston. But in the daily data, it can be hard to feel it, at least for now. Obviously, when it gets bigger, eventually you would, notice it depending on how big it gets, right? You might notice it every day. Um, IPCC does talk about signal to noise. Um, and here is, I think, an interesting visual, which is good context. They talk about it. When can you tell? And their point here is, when can you tell based on annual data, not on daily data? And so they've got bars that in the dark orange and the light orange this is kind of the range of natural variability in basically an average of high latitude location. And you can see that you can't really it annual temperature data has been within the normal noise until about year 2000-ish. We're finally breaking out, and you can tell if you look at annual data. Again, daily data, not even close, right? Low latitudes, even though the variability is a lot less, you'd probably see it earlier because they have less noise in the data, if that makes sense. To try to get a feel for temperature, here's another visual I made, which I just went and I found what's the July average temperature, um, day and night for a bunch of cities in the world, from Kuwait City down to Anchorage, and uh, show it versus the bar of 1.9 and that 4.0. And so if you're an engineer in Denver up here, or you're an engineer in Calgary down here, by year 2100, it's not like Calgary becomes Denver. And it doesn't move halfway to Denver, but it does move a significant part of the way towards Denver. I don't know if that provides any context or not, but there you have it. Another place, as I was grasping for context, is how does this warming compare to past climate? So here's another IPCC visual, and this is kind of temperature relative to 1850 and 1900, our reference point. If we focus on the orange line, you can see that the 2 points Celsius warming since pre-industrial puts us at about the same point as the last high in the last interglacial period. So this is us at a year 2100. This is again, that plus 4 degrees Celsius I talked about in the previous graph. Um, it puts us just a little bit hotter than where we were 100,000 years ago in that interglacial period. So if you were hanging around at the time, you were a caveman, the news report then would be, this is the hottest for the last million years. But today we often hear news reports that say we just had the hottest day in 100,000 years. It's kind of how warm we were compared to this interglacial spike that happened here. Keep in mind, people have only been around here for, at least people that can talk and write like we do for the last wee little bit, right? But again, I don't know what you do with this context, but there you have it, and there you have kind of what a 4 degrees Celsius timeline looks like, where you're back like 10 million years to get that kind of average temperature. So there's that context. Okay, let's talk about extreme temperature because the media is constantly talking about extreme weather events and extreme heat. And I think it's super important that engineers know what they mean when they say that. Well, I don't know if they know what they mean when they say that, but they're feeding something that they heard from someone else. But but here's where that comes from. So first of all, the IPCC is very clear about what happens in a warmer world. Changes in local surface temperature extremes closely follow the corresponding change to local average surface temperature. This is very important and fundamental. So it's what we've got is a shifting bell curve. We're not shifting to a different shaped curve that has a lot more extreme weather, as in hot parts of the bell curve. It's just a bell curve moving to the right. So if the hottest day of the year was 102 in 1950, it's like 104 or 105, today, if you're in Denver or something like that. Let's pause for a minute now to think about the media narrative you often hear. For example, you'll hear something like, in 30 years, we can expect to have 10 times the number of extreme events. So understand the math that would be going on in that calculation. So somewhere you draw a line that says what is an extreme day on your kind of current climate bell curve. And that's your threshold for an extreme day. And then when the bell curve shifts, you get more days that are above that threshold. So the more unusual the temperature was, the greater the multiple, if that makes sense to you. If you drew the threshold, you know, warmer than the hottest day historically, then the number of extreme days would go up infinity. If you draw the extreme day as fairly conservative, the number of extreme days doesn't go up by nearly as much. I find it to be a less useful metric for me personally, but I thought you as engineers or scientists would want to know what that place it feels like it's where science meets pablum, right? So know what they mean when they say extreme heat events. If you don't say it with the definition of what an extreme event is, it's not telling you anything. Um, just just to note and acknowledge that extreme years are a thing too. And there was extreme years in the 30s, for example, particularly warm. There were some extreme cool years a little bit before that. This is a plot put together by National Weather Service and NOAA. And it's interesting. It follows and shows the same kind of plots. I told you can do it yourself as well. You get kind of the same view. All right, that's what I was going to talk about with respect to temperature primarily. Now I want to go into storms, droughts, and all this stuff. This is going to go way, way, way faster because I think there's less to say about it. Let me tell you why. So the basic science for the water cycle is that, again, warmer water holds more moisture at a given humidity. So I talked to you before about 4% per degree Fahrenheit or 7% per degree Celsius. So at today's Earth's warming, which is about 2 degrees Fahrenheit, we should expect 8% more water vapor. The ocean, so here's the relationship that probably many of you have seen and worked with in the past. Um, so oceans drive evaporation, as I'm sure you recognize, on the planet. They are the evaporation engine. Um, so as our system heats up, the clouds off the ocean will contain more water. But land is warming faster than the oceans. And so that process could have a drying effect on the clouds inland. So the result is a warmer world, which is generally wetter, but it varies by location, and it can be tough to predict. So here's a cartoon to help you understand that. This might be obvious to you, but maybe not. So if you have marine air mass coming in, and you're living in a city with mountains behind you, and it's that time of year that the wind is coming, from the ocean to the land, and the weather is right for rain. So temperatures are going up. With that, the amount of moisture in the clouds is going up, so the rain would go up. And it's probably going up by a number very close to 8% right now versus pre-industrial. Whether it feels wetter or not, if you want to know how your dirt feels, it may feel wetter, it may not, depending on whether the warmer temperature is drying up that extra 8% of rain. So that's a little bit more difficult. It's certainly difficult to predict whether it's drier or wetter, whether the dirt is, but there's going to be more rain in your rain meter in this warmer world. On the desert, on the opposite side, it's more nuanced. So the temperature's gone up a little bit more than the person on this side of the mountain because you're further inland. The clouds had more rain going over the mountains, but they may not shed as much rain further inland as the land here is a little bit warmer, potentially drying the clouds a little bit more. So there could be more rain or there could be less, particularly depending on the direction of where the weather's coming from. Dryness will probably go up if the rain is kind of similar, but the temperatures are up. So it might be a little bit harder to grow a crop kind of in a desert. And it's often difficult in a desert, but it might be more difficult there. So hopefully that's sort of the opposing forces that tend to drive rain. And I want to pause here to contrast the difference between rain and temperature. So the IPCC has this really cool set of graphs, which I've shown you a case here for 4 degrees Celsius warming, which is hopefully, so remember we talked about that orange case being 4 Fahrenheit. This is 4 degrees. So hopefully we won't get that hot, but maybe we will. So the left image shows how much the average temperature, or the left top shows how much the average temperature will rise over the 3 months warmest time of year. And then the right image shows the hottest day of the year. And you see how these two images are about the same color and they look kind of the same. So again, this is a shifting bell curve. Fairly simple to think about. Now let's talk about precipitation. So the left image is the annual precipitation versus the baseline. So in this case, land temperatures have risen much more than the ocean. So for the inland, areas a long way from the ocean, average precipitation is not increasing, even though it's a warmer world. A lot of places it is, but a lot of places it's maybe 10% drier in the climate average. Again, this is a fairly extreme case. I'm going to show you other ones that are more like what we expect to happen. So these changes become more muted. But in an extreme case, you see, for example, interior North America being a little bit drier, maybe sort of like 10% drier or 10% less rain. But if you look at the climate extreme, there's big changes. So this is the wettest day of the year. Now, remember that water capacity increases 7% per degree Celsius. So at 4 degrees Celsius, the clouds should hold 28 more moisture. And so when conditions are right, big rains can happen. You can get 28% more rain. And that's about what you get here. You look at the color scale, on those extreme days, you're getting about that 28%. So there's nothing complicated. It's just basic physics there. But I want to point out the difference in character of the maps. So one of them is a shifting bell curve, and one of them is driven by weather. On an extreme day, when the storms are coming in off the ocean, wherever you're at, they skirt around the mountains and they nail you, you get the full brunt of the extra moisture. So when people talk about extreme weather and extreme storms, what they're talking about is basically this 20, 28, 30%, or in an extreme case, or where we're at today with 8% more rain. So the IPCC has a bunch of detailed images to show this in different cases. So here's one for 2 degrees Celsius warming. So again, this is about that happens to be about 2050 in the case that I talk about all the time. Where are we going to sit? So in winter months, as far as the amount of rain, you see most of the world is green. It's getting more rain, as you would expect. And there's a few places getting less rain. Most of them are over the ocean. And there's a lot of areas that are crosshatched. And crosshatched means that the computer models, a lot of the computer models are in disagreement about whether there's more or less. So they don't know about the sign of it. In other words, they don't know whether it's green or brown. So if they don't know if it's green or brown, they put a crosshatch. There's great transparency in their work here. So you can see in most of the United States, we can expect more rain in the winter. In the summer months, it's more nuanced and there's a lot more shading. So you can take your time and look at that if you're interested. So what do we get if we go to the National Weather Service plots? Again, you can do this yourself from the same website I told you. Just click on precipitation instead of temperature. I encourage you to do it. So I've got a 20% bar here I show on the right. So for kind of 6 Colorado locations, and they're just places that are of interest to me. So these are places along the Front Range, and then places in the mountains where you like to go skiing and fishing and stuff. And when you look at those, it's hard to see a trend on any of them. Can't see if it's raining more or less. And if you look at the average of those, you can't see the trend. And I think that's what you should expect based on the science there I discussed. In the desert, I told you maybe you would see less, and it would certainly feel drier. I plotted them. I think we're still in the maybe you would, because I can't see any trend. Go ahead, do it yourself. See if you can see some. The wetter cities that have a marine influence. Can you see something there? Maybe you can. Here's my average. Looks like it's going up a little bit. Not sure it's going up 20%, but maybe you're seeing the 8% that we should have now. I don't know. Looks like there's something. Plotted other cities just to show you can go ahead and do it yourself. Again, generally you can't see a trend. Soil dryness, I told you, is a little bit more nuanced. So the IPCC does predictions of that too. A lot of crosshatch because this is difficult, but there's some reasonable expectation the soil will be drier in some places. And you can see that on this map. Now I know this images here looks really brown, so you kind of think the whole world is going to be brown. I will remind you that plants are actually doing quite well. And here is again this NASA image. It's showing how the leaf index, how there's more leaf actions. If you look at the color, maybe there's 25% more leaf area in most of the world than there was in 1982. And and a lot of that's from the CO2 fertilization effects. And I think some of it's from slightly warmer temperatures in the north, which allows the Arctic areas to have a little bit more leaves. So just because the previous slide was brown doesn't mean the Earth is brown. um, Earth is still got a lot of green, especially if you're creating this image here. Um, just a note about the CO2 fertilization effect. I don't think I've talked about mechanically what's happening. Um, I think one thing is that plants have these little pores where they take in the carbon dioxide and they open those pores more or less, depending on how much they need to inhale, how much they need to breathe. And when there's less carbon dioxide or more carbon dioxide in the air, they don't have to open those pores quite as much. So they don't lose quite as much water from transpiration. Um, Plants lose a lot of water, right? Like if you walk around on grass, it's never hot on a hot day, right? That's because the plants are they're taking water out of the ground and they're transpiring all the time. If there's slightly more CO2 in the air, those little pores are slightly smaller, and so they're transpiring slightly less water. So they have this slight offsetting effect as far as, a drier climate might not necessarily hurt them as much as you would think. But obviously that's work in progress, and it's apparently an effect that varies by plant. So some plants are more resistant to climate change and some are more vulnerable. Anyway, that's just a little comment about soil dryness and plants. All right. So how much worse will storms get? This is super hot topic. You hear about it all the time. Every bad media story talks about these storms will increase with climate change. So in IPCC chapter 11, they have this really interesting graph, and that shows how much moisture we should expect in a typical part of the world on an extremely high precipitation event. So in purple, we have a 10-year event, and in brown, we have a 50-year event. So 50-year event, that's a big storm, right? That's a once in a lifetime storm for a given place. Um, so and it's also a box plot. So you can see kind of their range and expectations and their midpoint. The boxes are 66% uncertainty lines and the whiskers are 90%. So today, today at 1 degree Celsius, so we're just a little bit above one. So this is slightly understating it. At 1 degree Celsius, we would have 7% more moisture, right, in the atmosphere at a given humidity. And it looks like the 50-year storm, it's about maybe 8% worse. So it's conforming directly with the amount of moisture in the atmosphere. I think that probably makes sense to you. At 2050, in that 4.5 watts per meter case that I talk about a lot, when we're 2 degrees Celsius warmer, storms should have 14% more rain, right? 2 times 7. And it looks like it plots at around 14%. So that would mean a storm that would have 5 inches of rain has 5.7 inches of rain. So signal to noise, in a neighborhood, if you got 5 rain meters, they might vary by that much too. So I think there's going to be more rainfall with storms, and this captures it. But it's not like the storms are 100% worse. I think some people worry that with climate change, the storms are going to dump twice the water than they were before. I think you can quickly calculate for them what they should expect. If doesn't mean a storm won't dump twice as much water on you, it absolutely might. That's weather. And I think it's possible that certain, changes, in a particular place due to climate change scenarios could make a place particularly vulnerable. But I don't think that's typical. I think what you see here is what is the default expectation. So you talk about extremes. If you're living in a town that has, the water diversion system that's designed for a 6-inch rain, and the 50-year storm has been, a 5.9-inch rain, then this is a big deal. You're suddenly very vulnerable. Um, and so, obviously engineers need to take that into context too. Um, Hurricanes. Let's talk about hurricanes. This is an interesting topic. When I did this presentation for the SPE group a couple of days ago, Hurricane Milton was bearing down on Florida. So it felt out of touch to be kind of talking about this. But again, I think I'm saying that it's not maybe the biggest news in climate. Um, and although hurricanes are always big news. So the three things that you want to trigger a hurricane to make one happen are you want warm oceans, particularly warm ocean day, and a particularly cool air mass that's sitting on top of the oceans. And then you want minimum wind shear. So that's kind of the horizontal layers, which would cut the top off a hurricane when it's trying to develop. These are the things that you want to have if you want to set up a hurricane. So what happens with climate change? Um, think about that a little bit. Um, the oceans are warming. Check that box. The oceans will get warmer. So that will be positive for more. You want to have a cool air mass on top of that ocean. Well, when you get those, I think that can often be you've got a cool air mass coming from a continental area over the ocean. If the continental areas are warming faster than the oceans, I think you're less likely to get a cool air mass that's differentially warmer than the oceans. So it's not obvious that you get the cool air mass box checked as often as you did before. And then wind shear is something that's complicated. I've certainly read that with climate change, we might get um, less minimal wind shear. So we might get more wind shear. I haven't read a lot about that, but the bottom line is it's not obvious that we would have more triggers to make more hurricanes with climate change, particularly when the Earth is warming. Um, maybe many hundred years from now, if we actually go through cooling cycle, we might actually have a lot of hurricanes then, because then you could understand why that trigger would be more likely to happen, if that makes sense. Um, Now you can so I think most forecasts, including the IPCC, say that they don't expect more number of hurricanes because of climate change. And they will also say that there is no observable trend in the number of hurricanes in the US. Although from year to year and even decade to decade, there's all kinds of changes. But in the long run, they don't see that it's increased. Storm intensity might be a little bit of a different matter because again, the energy in a hurricane is basically from the latent heat of the water, the moisture condensing. Uh, and the moisture is coming from that warm ocean, moving up through the colder air, um, driving the forces that make those high winds. So I think it makes sense that you would have less hurricanes, but the ones you have would be a little bit stronger. The math in hurricane intensity surprised me when I read it that they won't be that much stronger or as much as you think they might be. Um, and I think it's has to do with a bunch of hurricane math that I followed, but I got lost in some of the engineering was pretty complicated. Um, but it sounds like maybe you end up getting about 5% higher wind speed in a bad hurricane in a reasonable climate warming scenario um, than where we've been. So that's the math behind and the story behind hurricanes. Um, I'm not sure they're the biggest story with climate change, although they will always be the biggest news item when they happen because there's such a human aspect to it all. Sea level rise. I think this is a news story too, but this is a real long-term news story. Um, let's talk sea level rise. Um, First of all, sea level rise to date. It's been about 4 inches since 1970 and about 8 inches since 1990, per the IPCC work. And to me, it looks like good work. It's like good numbers. In context, that pace is about 1 inch per decade. Um, that's a useful number for a future slide here. Um, Land masses are moving. So put that in context. Some places land masses are rising, some places they're sinking, some places they're sinking kind of rapidly. For example, New Orleans, I think, is dropping by about 3 inches a decade. Um, so you can kind of superimpose those two. So you end up having a 4 inch per decade problem with sea levels there. And other places are still uplifting, from the receding ice from the last ice age. Um, I think where we sit today, wind and tide dynamics are a much bigger story about, what kind of surge you get or what kind of sea level problem you're having at a certain place. Um, if you're looking at future warming or future sea level rise, it's a component sum calculation between temperature, warming the ocean, and basically thermal expansion. And then the other is uh, melting seawater, melting ice over land masses. And the IPCC does a component sum calculation, and here it is. So you basically have got ocean warming at the top, and then you've got land ice storage here, and you can see how it's built up to today to get to that 8 inches where we're sitting at today. In context, if we should step back, sea levels have changed a lot. Um, at minus 50 meters, you can walk from Alaska to Russia. Our 4 inches rise over the last 50 years is about 1/10 the width of this blue line here. So uh, it can move a lot compared to how much it's moved. Um, and 1 inch per decade, which we have now, um, it's probably moved a lot more coming out of some of those ice ages before. There used to be a lot of ice around. Um, So let's talk about how you do the calculation yourself. Well, you have to look at how quickly the sea level is warming. So here's a graph of sea level warming versus land warming, so you can see the temperatures are coming up, but you can't use the average global temperature. That's wrong. You have to use a slower amount of warming because it takes longer. And you also have to look at it by layer in the ocean. So basically what you do is you just take the volume of the ocean times the thermal coefficient, um, times how much of the ocean is in each of these layers, and you make estimates about how much they're warming up. You can do it yourself. It's easy to do. Um, and you need to superimpose that with what's happening with melting ice. So let's talk about that. Um, Ice cap melting is perhaps more interesting because it's also more uncertain. Um, Here in the top right, I've got the total amount of water stored on land ice. If it was those ice masses were to melt and basically run into the ocean. So if all of Antarctica was to melt, that would be 190 feet. Greenland would add 24 feet and glaciers another foot to get you to 215. Um, with satellites, it's very easy to measure what's changing in the amount of land ice, basically by digitizing the surface, and you can just do volumetrics. The tricky part is making the projections. Um, there's a wide forecast uncertainty, particularly around the Antarctic. And a little cartoon on the bottom make it kind of obvious why Antarctica is so uncertain. And because remember, this warmer world has more moisture. So it's likely that Antarctica is going to have more snow. And so that will be increasing the amount of ice on Antarctica. At the same time, there's going to be more melting, more iceberg calving and things like that, which would reduce the amount of ice. And so it's sort of the teeter-totter between those two effects. And so you end up modeling weather, and weather is always difficult. So that's why these ranges are much different than the temperature ranges. Remember, we talked about plus or minus 30%. So here's our mid case. I'll show that. This is the 4.5 case. And this is by year 2075. here's where they sit. From glaciers, you might get between 1 inch and 5 inches. Um, Big range, probably some of the same problems as you have in Antarctica, right? More snow, but more warming. Greenland and Antarctica combined 2 to 20 inches. So instead of plus or minus 30%, you've got an order of magnitude in uncertainty. It's great that the IPCC is so transparent, right? We kind of see where the future might lie. If you combine the thermal with the thermal expansion with the, uh, the ice melting, you can plot them up in feet, and I think it's helpful. These are the P85, P15 numbers. So again, there's a wide uncertainty, but we've made them a little bit smaller by showing the numbers where there's a 5 out of 6 chance that the numbers are right. It says in the last 50 years, it's been 0.2 to zero point 0.4 feet. We kind of know that. Next 50 years, look for another third of a foot to 2/3 of a foot. And we've gone way out longer term here. By 2050, we've got 2 to 4 feet. Um, so I think, you would say it's not our biggest near-term problem, but long-term, this starts to get more serious. We're getting into several generations here, but it definitely gets more serious and will eventually get a lot of attention. Um, all right. So I want to kind of close this kind of with two thoughts, which I think are important for context going forward. The first is the idea of carbon budgets. You'll hear a lot about that um, if you follow climate media and things like that, and climate press releases. And it has a lot to do with how much carbon can we emit before the world is expected to warm a certain amount. So you hear a lot about the 1.5 degrees Celsius target. So here are future amounts of emitting for different IPCC percentile numbers. So for their 50th percentile case, which I guess is kind of their midpoint, we can emit 500 gigatons more carbon from 2020 before their middle case gets us to 1.5 degrees Celsius of warming. So right now we're at 41 gigatons a year, right? So 4 years have passed. And so we've used up some of this, and that's why there isn't much time before we will obviously exceed the 1.5 degree target. That's why you'll often read that people are press releasing, wow, looks like we're going to exceed 1.5 degree and we won't make our target. That's where this target comes from. And then obviously, if you increase your temperature, that you're wondering how much will be emitted to get to that temperature, you get, for example, at 2 degrees Celsius, you get a much larger number. And if you take 1350 divided by 41, you get many more years of emissions to get to 2 degrees Celsius scenario. And also note, because of these percentile numbers, you can see that, for example, if you emit 900, there's a 17% chance that you will warm up. You could be lucky and you've only warmed up 1.5 degree because there was remember that plus or minus 30% bar thing. But there's also a chance that you might warm up too if you're particularly unlucky. So that's, anyway, carbon budgets, that's the context around that. And people think a lot about that, I guess. And the other thing I wanted to do is go last slide, which I think sums up a lot of the work I've talked about here. And I'm kind of showing two opposite perspectives that you could take away by doing math. So on the left, it's our second example case. So if all USA human activity paused for 50 years, a typical US land location would end up warming 1/4 degree Fahrenheit less than if we simply kept going as we were for 50 years. So in other words, if all of US peoples disappeared and it didn't change what happened in the rest of the world, um, we would end up only being cooler by a quarter of a degree Fahrenheit. I think when we did the example we did in Celsius, we had 1.5 degrees Celsius. So it's a quarter degree Fahrenheit, whereas the average city changes by 20 degrees Fahrenheit. So, the differential impact of our activities seem very small compared to normal weather variability. And I think it can feel like our efforts, have very little effect. Um, on the right, using our basic equation again, I'm going to move my picture out of the way again here. Sorry about that. Um, we're showing global average surface temperature here. So this is not on land. This is everything put together in degrees Fahrenheit. And I've kind of got an arrow there that shows in where we'd be in 100 years. From this, I think if we don't act, the planet will get much warmer and sea levels will rise very materially. I think that's also obvious. That is, if the larger human race doesn't find a way to self-correct, the world will eventually be totally different and much warmer. So obviously, some smart engineers and scientists and entrepreneurs going to have to make some breakthroughs. There's no way around it. We're going to have to make big changes, right? Um, and how long that takes will determine how high up this curve we walk before we're successful and all that. So there must be 100 different directions that you can run with these, examples. And I'm going to resist the temptation to editorialize any one of them. And I'll leave that to you, my fine audience. I will encourage you to make your own calculations and scenarios so that you'll have a better feel for the whole thing. And I certainly hope that in this time you've learned some things that you didn't know about climate analysis, and that your appetite is whetted to learn more, and that you'll pass your learnings on to other people, and we can make climate more of a quantitative, pragmatic discussion going forward. Thank you for your interest.